All right. So this course, trigonometry, is where we're kind of starting. So this is a little bit of a convergence of topics from geometry and topics from algebra. So we're going to start here with just a little bit of an overview. So this is stuff that's like not things that I would ever test on, and it's not things that are necessarily in like the lesson that are already typed out for you or whatever. I just want to give like a little bit of a framing as to like what we're about to start working on, so it gives you a little bit of a picture of kind of where we're going. And then we'll start like the actual content, okay? So I just want to frame the course a little bit, because the first semester is, the majority of first semesters, we're kind of working on building something, and it helps to get a picture of kind of like, okay, where are we starting with and what are we trying to get to? You know what I mean? All right. So when we look at the word trigonometry, what is the root or the prefix that we see there, I guess I should say? Yeah, you see the trig here, which should probably indicate to you triangle, right? So trigonometry is kind of foundationally talking about triangles. So if you think back to your geometry course, what are some things that you talked about that were specific to triangles? Again, there's no like right or wrong answer. Just shout crap out, you know. Anything.
Side angle side. Okay,
so side angle side was a theorem that there's actually two versions of side angle side. So side angle side was talking about their side angle side congruence, and then there was side angle side similarity. And these were one technique to prove that two figures were similar or congruent. So of those two, the one that's going to be the important piece with respect to trigonometry is going to be the similarity idea. So if you remember, we say two figures are similar. Let's say we have a 30, 60, 90 triangle that looks like this, and another 30, 60, 90 triangle that looks like this. We know that these two triangles are similar because of angle-angle similarity. That's one of the similarity theorems. Now, I'm using a lot of vocabulary here and a lot of theorems. If you don't remember the specifics of these, that is okay. The geometry specifics that I'm dealing with right now are not critical. Okay, I'm just kind of talking about the foundational pieces that we're using. You wouldn't actually use these pieces to do any trigonometry. I'm not going to ask you to prove that triangles are congruent or similar or any of those things during this course. So don't get freaked out. But hopefully the things that I'm talking about are at least like familiar sounding. If you're at like, oh yeah, that sounds like something we talked about, that is okay. So we say two figures are similar if all the angle measures are equal and the side lengths are proportional, right? So for example, if these are sides A and B here, and these are sides C and D, then the ratio of A to B should equal the ratio of C to D, right? That's what similar means. Is they're like, okay, everything has the same angles and the same proportions, right? Like this triangle is just like 3 times as big as that triangle or whatever. You guys, that sound familiar?
Yeah.
Yes, thank you. what else do you guys remember with regard to triangles? So similarity is an important concept that we'll be using to build upon. Josh?
Sohcahtoa.
Yeah, and this is directly related to similarity. So Sohcahtoa was your acronym that you used to remember the relationship between the side lengths of a triangle and the values of the function sine, cosine, and tangent, right? So in your geometry course, you defined sine, cosine, and tangent on a right triangle. And the sine, cosine, and tangent operated on one of the acute angles in the right triangle. And then relative to the angle that it's operating on, we were able to calculate the values of sine, cosine, and tangent using the lengths of the sides that were adjacent to the angle, opposite the angle, or were the hypotenuse of the triangle. So the SOH in Sohcahtoa tells us that sine is opposite over hypotenuse. The cosine tells us that cosine, or the ka says that cosine is adjacent over hypotenuse. And the tangent of theta is the toa, which tells us that tangent is opposite over adjacent. Is this all still familiar? Again, if you're like, I don't quite remember that, that's okay. It's okay. Again, we'll redo most of these pieces. We're just kind of talking about where we left off and kind of where we're looking to get to. Everybody's okay with this so far? Okay. So these were the two big triangle ideas. You guys nailed it with your first two suggestions that we want to build from. Here's the idea though. So sine, cosine, and tangent, as we originally defined them, required a right triangle, right? We want to shift that definition and get it so it doesn't require a right triangle. So we want to expand our definition so we can use sine, cosine, and tangent on any size triangle. Now, if you were in the honors geometry class, I think you did that for sine and cosine. Do you remember that? Yeah. So, you could use the law of sines or the law of cosines. Was a way to use sine or cosine inside of non-right triangles, right? So you could do sine of a obtuse angle or cosine of an obtuse angle, right? And again, I'm not worried about what those formulas are. We'll redo that stuff when the time is appropriate in the course. So, and we'll do it in great detail. So not worried about that right now. But these are things that you probably mentioned. But what if, okay, but in your geometry course, like when you talk about an angle, you're always talking about this part of an angle as opposed to this part, right? Everybody agree with that? Can you think of a real-world setting in which the blue part is the piece that we would need? It's not obvious, but it's real. So imagine you are doing some kind of navigation. So you're flying a plane or, piloting a ship like a boat, or even you're walking across like a field. In any of these settings, since nothing is really laid out on a grid, like left and right don't really make a great deal of sense, right? Depending on where you're pointing, a left turn or a right turn what does that mean? So say I'm trying to go from here to here. Going one way, we're talking about like doing this angle. But to go the other way, I'd either change the orientation or I'd be talking about this angle, right? To go back where you started. So it's either a situation where we're flipping the orientation all the time. Like that makes for a terrible system to try to navigate and tell somebody how to get there. Where it's like, oh, well, now you flip the orientation. It's like that's terrible, right? Or you have to allow for situations where you're talking about the other half of the angle, right? So the next thing that we're going to want to do, we've extended sine cosine so that we can do it in non-right triangles. The next thing we'd want to do is extend sine and cosine so you can do it on angles that are bigger than 180, angles that it's impossible to even make a triangle out of. So we're going to start by then taking sine and cosine outside of the triangle and define it on angles that are impossible to be in a triangle. Everybody okay with that? After that, we're going to want to say, okay, what about, hi, Mr. Simmons. No problem. After we've done that, we want to talk about, well, what about angles that are even bigger than 360? That are more than a full rotation. And you might think, why in the world would you want to do that? Well, imagine you have a machine that has a part that rotates, like the drive shaft for an automobile. And you want to know like how many revolutions this thing makes in a second. Well, you're talking about an angle that's bigger than 360 degrees there, right? If you're talking about multiple rotations. And lots of machines have spinning parts in them. Anything that has motion involved with it really has a spinning part to it. So all of a sudden, that becomes a really valuable thing. So angles that are bigger than 360, we want to extend our definition now to be able to cover. And now if you have a car, when you put the car in drive, the drive shaft spins one direction. When you put it in reverse, it spins the opposite direction, right? So we're going to want to have some way of defining a difference between rotation one direction or rotation the other direction, right? So we'll also want to define a negative angle, which again, like from a geometric perspective, doesn't make a lot of sense if you're talking about an angle with a negative measure. But when you talk about a real life setting, it's like, yeah, we need something to indicate direction. Negative is the kind of the obvious way to do that. So we're going to, the next thing we'd want to do is extend our definition for sine and cosine so we can contain angles that are bigger than 360 and smaller than 0. And once we've done that, now we have a situation where I can take the sine, cosine, and tangent of any number, right? You can now take the sine, cosine, and tangent of anything, any number you name, I can calculate a value for that. And that's most of what first semester is going to be doing, is building, continuing to extend our definition of sine, cosine, and tangent from like right triangles out of the triangle and into this bigger three-dimensional world where you can really have angles of any size. And really, you're getting away from an angle in general, right? We're extending this definition so it still encompasses everything we had before, but includes more and more and more and more. So that's kind of the idea for first semester. That's kind of what we're building, okay? At the end of first semester and into second semester, then, we'll look at systems that also have the same kind of structure that we built in first semester. So we'll talk about vector systems and polar coordinates and other, some of these other systems that have, or some other representations that use the same or an analog of the same system that we've been building. Okay. So before we do that, before we get to that, chapter 1. This is going to be a review of some important algebra concepts that'll kind of come into play. What we're going to be doing in chapter 1 is talking about functions and graphs and some properties of these, because sine, cosine, and tangent, the three main things that we're going to be interested in, excuse me. The three main things we're going to be interested in this semester are functions. And we're going to want to have a graphical representation of these functions. So we need to go back and just kind of review these fundamental algebra representations. Okay? Most of what we're doing here, in fact, I think all of what we're doing in first semester are things that you did in your algebra class from last year. So depending on how good or bad of a teacher you had, I'm doing this because I was the teacher for, I don't know, probably at least half of you guys, so it's on me if you don't remember. But most of this should be kind of review. So if this feels easy, that's good. If it doesn't feel easy, that's okay. I'm going to do it again. So let's start with the definition. The most fundamental definition of algebra is for a function. Does anybody remember the definition for a function? Okay. So it's a set. There it goes. What happened here? This happens sometimes with the new stylus here. I don't know why. I'm just going to restart OneNote real quick. Nope, it's still doing that. What happened here? Guys, I am technology. What happened to my yeah, I mean, like, but here's the thing is, like, my stylus shouldn't be connected to what's going on up there, I see. Right? Like, but somehow my stylus got, like, but now it's like I'm not on the screen and it's writing. Yes. It ends in 2 minutes anyways. Oh, okay. Well, we did a good job today.